Hello and welcome to another measurement and instrumentation class. In the previous class, we spoke about different type of measurement tools. We gave some examples. Today, we will focus on analog to digital conversion, noise and noise reduction, sampling rate, and the effects of sampling rate on measurement, and a little bit continuing on different type of transducers. We already started with transducers. We gave some examples of different types of transducers, active and passive transducers. And one example was the microphones and the speakers. Again, transducers are a type of instrument that converts one type of energy to another. So for example, it converts mechanical to electrical, like a voltage, or voltage even to current is considered a transducer as well. And today, again, as mentioned, I'm going to continue that and continue with noise and sampling rate and analog to digital and digital to analog converters. Now, another type of transducer is called the resistive transducer, or what we call a potentiometer or POP. There are different types of potentiometers. You can see here three types of potentiometers. We have the translatory, the rotational, and the heliport. All of them use the same principle. We know that for a resistor, and I already mentioned this, the resistance of a resistor R is going to be equal to rho L over A. So the longer the element is, you're going to have a higher resistance. So imagine if I put a resistor, I connect one end of this resistor to the positive, and I connect the negative part to a movable or variable type of rail or contactor. If I start moving this right and left, I can decrease or increase my resistance. So if I move it to the right, and if I have it at point A, and in the middle is point B, and at the beginning it's point C, which point would give me a higher resistance? A, B, or C? A. So RA is going to be greater than RB, is going to be greater than RC. Why? Because for the electrons to pass through and get to A and get back, they have to travel a longer distance. Therefore, L is higher, LA is higher than LB, it's higher than LC. Therefore, we're going to have higher resistance. And for all of these three, we have rho, the material is the same. The thickness, which is A, the area, is the same. So the only thing that is changing is actually the distance that is traveling, or the length of our resistor. Now, using this principle, we can sometimes twist it. We can make it a circle. We can make it linear and create different types of potentiometers. Depending on how much space we have, if you have limited space, you can't put a linear one or a translatory one. It's going to be, too long. So you're going to put a rotational or a heliport one. But the linear ones, actually the translatory ones, also have their own application. If you have a very high voltage and you want to build a huge resistor, a high power resistor, you can't usually build it in a heliport system. Those, you need a thick wiring and a thick resistor, so it's sometimes easier to build it in translatory. An example of the translatory or heliport potentiometers, and I'll show you some examples in the lab as well, is going to be if you have any old radio in your car or at your home, you would see that volume knob that locks in place. You have a minimum and a maximum. That's usually a potentiometer. And that potentiometer is connected to an op amp, and it controls the amplifier's gain, and therefore it controls the output voltage that you give to the speaker, and therefore the volume of the speaker. And it's the same if you are using a radio and it has these round knobs. By changing this resistor, you're changing the RC and the filter, and you're shifting the filter, and you're picking a certain station, an FM station. Newer ones are using digital. They're not using any analog resistors and potentiometers, but these potentiometers are still in use in a lot of different applications as well. If you want to build a filter, it's going to be a great option. Any type of, again, amplifier, if you need a variable resistor to control the gain of the amplifier, you can use a potentiometer. May I ask, how many of you have already passed LIC, linear integrated circuits? Okay, so in LIC, you know that, for example, if you have an inverting amplifier, the gain of that inverting amplifier, and it looks something like this, and this is our input, and this is the feedback resistor, and this is the output resistor R2 and R1. Now, and this is the ground. Now, the gain for example, an inverting amplifier, and the reason that we call this an inverting amplifier because the input is connected to the inverting input of the amplifier, or the negative, it's going to be equal to negative R2 over R1. Okay. Now, if I replace this R2 with a potentiometer pot, I can adjust this R2, therefore I can have a variable gain at the output. So imagine if the input is a sound signal and the output is connected to a speaker. By adjusting this resistor, I can adjust the volume in the speaker as well. It's an easy amplifier that you can easily adjust the output. So these, again, as mentioned, resistors, potentiometers are used a lot. Now, the resistive potentiometer are used in control systems in adjusting resistance or amplitude, or the gain of a system, or even in a filter. They are also used as a type of sensor as well. And before I continue that, you're already familiar with this equation. What is this equation? This equation is used when we use a voltage divider. And a voltage divider is basically when you connect a resistor, two resistors together. If I connect them like this, I'm going to have R1 and I'm going to have R2, two resistors. And then have the source connected here, positive and negative. If I want to measure the voltage here, V2, I can use the voltage divider principles. So V2, or if this is our V out, is going to be equal to, which is V out, it's going to be equal to R2 over the summation of the resistors, R1, R2, times Vs, which is the source voltage. Now, if I want to find VR1, it's going to be R1 Vs, R1 plus R2. So if I start moving this needle up and down, I'm reducing one and increasing the other one. Therefore, I'm adjusting the output voltage. So by moving the needle, moving the potentiometer knob, I'm changing R1 and R2. Therefore, I'm changing the output voltage. Now, from here, what is the maximum that V out could be? I'm going to give you this as a practice problem. You're all familiar with voltage dividers from AC/DC analysis, circuit 1. Let's say we have the one on the left, so the translatory, and this is at the middle. This resistance is 10K. Total resistor is 10K. I want to find the output voltage at A, B, and C. So at 3 points, A, B, and C. So if this moves to A, B, and C, and my input voltage Vs is 20 volts, I want you to find VA, VB, and VC. I'll give you 5 minutes to think on this and I would solve it. By the way, the first student to solve this gets extra points on their first homework. And this could be the same as the rotational as well. So imagine this is also 10K, and imagine this is in the middle, and this is A, B, C. Does anyone have the answer? Yes. Okay, what is the answer?
20, 10, and 0 respectively.
Yes. Perfect. VA is what?
Sorry.
What is VA again?
20.
20. Perfect. And what is VB?
10.
Perfect. That's correct. And what is VC? 0. Perfect. Without even calculating it, you can find. So VA, the voltage between these 2 points, because it's parallel with the source, it's going to be equal to VS. So VA is equal to VS, which is 20 volts. And VC, you don't have any resistance between here and the ground. So VC is going to be equal to 0. And VB is half, because it's in the middle, as I mentioned, it's half. So VB is going to be equal to half of that 10K is going to be 5K. For R1 is 5K, and R2 is 5K. So it's going to be 5K over 5 plus 5, which is 10, times VS, which is 20, gives us 10 volts. So 20, 10, and 0. So if we use this, for example, for an amplifier, the voltage of the amplifier could go between 0 and 20 volts. So if you want an example, if it's connected to a speaker, it could go from, complete silence to the loudest, which is 20 volts. Now, the transducer, as mentioned, can be used to control, to modulate, and the feedback of an amplifier to control its gain and the output, and to modulate the output. And also it could be used in filters as well, to adjust the filter and its cutoff frequencies. But these type of transducers could also be used as a sensor to measure things. One example is to use these resistive transducer to measure a fluid level, liquid level. Now, this is a very common popular type of sensor. It's called the fluid level sensor with the float. Basically, you have like a floating ball attached to a rod, and then at the end, it's attached to a variable resistor. The higher the fluid the ball goes higher, and the transistor actually goes the other direction. So you're going to have more. And by measuring this D to D ratio, we can measure and calibrating it to the fluid level, we can find out how much fluid we have in this tank. This is actually used in, probably it would be in your gas tank of your vehicle. If you take out the gas, the pump inside the gas tank, you would see that it has a little arm and this type of floating. Toilets don't use a sensor, but if you had a sensor, yes. Yeah, it's going to be exactly like that. But it's the same principle. Yeah, good thing. Yeah, it's the same principle. This has some limitations. What is the limitations? Can you think of a few limitations of this system?
It's not super precise.
It's not super precise. Yes, that's correct. Sometimes it's okay if you want to measure, the amount of gas left in your gas tank. You don't want to be down to the milliliters, but it shows you very good. But yeah, that's correct. If you want to measure something that is few, cc's or milliliters, it's not going to do that. Another problem is that this has a limited amount of movement, okay? So the maximum that could go high is like this much, and the minimal is maybe this much, okay? So you have a limited amount of movement. So if you have a very tall tank, very, very large tank, you can't use this. Imagine you have a tank, these huge oil tanks that are in these oil refineries that are like maybe 100 feet tall. Some of them are 150 feet tall. Then you can't use this. It's going to have limitations. Then we go for these ultrasonic. If the tank doesn't have, it's a sealed tank, like you're going to, it's like a liquid nitrogen tank or a liquid gas tank. You don't want to put a hole in it and have the other side sticking out. And you won't have electricity, any type of current around that tank. This is not going to be good because you have a little bit of, if gas leaks a little bit, you're going to have an electric signal. It's going to ignite and it's going to be dangerous. So we go with the ultrasound one that we saw in that in the rocket that we saw before. Where is it? Yes, this type of ultrasound transducer. And one thing that I have personally experienced is, so for example, this type of sensor, if you're going up a steep hill, then the liquid moves to the other side of the tank, and suddenly this drops. And you may think that now the tank is empty or full. If you're in an incline or something like that, you park somewhere, this sometimes is not that accurate. But other than that, it's very reliable, very cheap, and it's going to last a very long time. And the voltage, again, using the voltage divider principles, across the Viper of a linear pot is proportional to the displacement D. So V is going to be E, which is the source voltage, D over capital D, where D is the full-scale displacement and E is the voltage across the pot. Another useful application for this is going to be linear actuators. So if you have a linear actuator, which you want to open and close the door, you can put a linear pot or resistive transducer in and connect one pot to the end of the actuator. And when this actuator arm moves, you can determine exactly by measuring the resistance, you can measure the distance that actuator is traveling. So you can find out if the actuator is fully open, the door is fully open or fully closed or halfway. You can determine that by measuring this type of. So there are a lot of applications for this. Let me give you a small example. If E is 12 volts, D is 50 ohms, and this small d is 15 ohms, I want you to find the output voltage. What is the output voltage V? Again, this may be a question that you have in your first exam. So E is 12, D is 15, and capital D is 50. What is the answer? Yes, 3.6 volts. It's going to be 180 or 550. It's going to be 3.6 volts. Okay. Now, if the output voltage is 0 volts, so in this particular case, if the output voltage is 0 volts, what does it mean? Is it full or empty? So imagine this is exactly the one that you see on the left. And this is connected to your E. And the voltage, the output voltage that you see here, which is connected to this, is showing 0 volts. Is the tank empty or full? Full. And what if it shows 12 volts? It means it's empty. So the lower the voltage gets, it's becoming full. Okay. Now, another application for this resistive potentiometer or resistive transducer is for measuring pressure. This is an example of a resistance pressure transducer. And you can see we use the same principles. We have a spring, we have a resistance contacts, we have the resistance leads to external bridge circuits. And you can see that we have a pressure inlet, we have a diaphragm or bellows, and then when the pressure hits, it moves this in the spring, and this part is actually a linear resistance, and by moving up and down, we have a change in the resistance, and we can measure how much pressure that we have. This is used in a lot of applications. For example, if you want to measure tire pressure, air pressure in your tire, oil pressure, a lot of applications. On the left, actually this one on the left is mainly used a lot in liquid pressure like oil pressure, and the one on the right is used for measuring air pressure. So on the right, again, a different design. You have a diaphragm, you have the pressure inlet, you have the spring again, movement of the spring moves the contacts, and then the resistance between the leads would change. Usually we give this to a Whitson bridge. I'll explain what the Whitson bridge is. So that's the reason it says connected to external bridge. And again, on the left is the resistance pressure transducer, and on the right is the sensitive diaphragm type of transducer. Now, depending on your application, if you have low pressure systems, you can use the right one, even for liquid. But if it's very high pressure, it's going to, rupture the diaphragm and destroy the sensor. That's the reason some of these sensors, they have a pressure limit. If you put it on under too much pressure, you're going to break the sensor. Any questions about this? No? Okay. This is another type, as mentioned, a linear actuator. You can measure the displacement using a wiper or a movable contact. And then you have the displacement and the movable arm of the pressure element. And all of that, you have a multi-source for it, which is the bridge power supply. And here we have a bridge, which here is a Wheatstone bridge, and you would measure the output voltage. The important part is the resistance or transducer itself, and this in the middle, which measures the output voltage or current. Now, linear actuator is a little different from a servo motor or a step motor. Step motor, servo motor, they would define the movement in a different way. So this is completely, I don't want you to confuse this with, if you can build a movement sensor with a servo motor or a step motor, those are very accurate. They can measure down to like 0.8 degrees of movement. These linear actuators are for different, other different purposes as well. This is an example of another type of transducer. Again, we have a shaft, we have the conducting strip, and we have the wiper and the contacts. But all of them, again, use the same principles. One problem with these resistive transducers is that these contacts wear after some time. So, if the movement is too high or you have a lot of shaking, after a while, it's gonna, rub against each other and it's gonna wear them down. Another problem, if you have very high voltage or very high current passing through these, it's gonna work like a welding. You have a lot of sparks and it's gonna weld them together. If you have had any of these drills that use a regular DC, not the brushless DC, and you could look at the back, it's going to create these sparks. And the commutator, if you don't replace those, it's going to, eventually wear out and destroy the motor. So that's a little problem.